So our discussion last time ended kind of in the middle here with the discussion on hydrogen peroxide. And with hydrogen peroxide, we were looking specifically at just kind of some of the common uses of hydrogen peroxide. And so we said that our uses for hydrogen peroxide kind of ranged from general antiseptics, where we can kill bacteria, clean out wounds, all the way to rocket fuel, where we can use it to do some of the high energy capacity needs for space travel. Now, regarding hydrogen peroxide itself, the substance is pungent. It's got an irritating kind of odor to it. If you get a fresh bottle of hydrogen peroxide and just walk up to it and give it a good whiff, you'll get a little bit of that tingling sensation in your nose. And keep in mind, that's only a 3% solution. At the higher concentrations, that effect becomes much, much more profound. Now, here's the thing that's really bothersome with hydrogen peroxide. Hydrogen peroxide decomposes relatively easily. It's unstable. And when it decomposes, it turns into water and oxygen gas. This decomposition happens naturally on its own, but is accelerated when it is exposed to ultraviolet light, sunlight. And so as a result, you'll see that hydrogen peroxide gas is almost always stored in a brown bottle. The brown bottle blocks out the sunlight and keeps that hydrogen peroxide stable for longer. Now, even at that, we know that hydrogen peroxide does eventually decompose. It does so on its own. Those peroxide bonds are unstable. So it really doesn't matter how much we do it. It's going to eventually just break down. And that's why expiration dates on things like hydrogen peroxide really need to be followed. Because the expiration of hydrogen peroxide is not necessarily going to leave some sort of toxic material inside of the vessel, like might what happen with certain types of other medications. But it loses its effectiveness the longer that it sits in that brown bottle. So if you ever notice, you get an old bottle of hydrogen peroxide that hasn't been opened for a while, and you open it up, the first thing that you notice is that it hisses at you. The reason why it hisses, that oxygen gas that is just sitting in there as a product of that decomposition finally has a way to get out. And it gets out. That usually is a pretty good sign that your bottle of hydrogen peroxide isn't as much hydrogen peroxide as it once was. You basically have a big brown bottle of water. Now, at concentrations greater than 20%, we not only see that we can have those small scale kinds of effects, we can also see severe skin irritation. It just bugs the crap out of your skin. Kind of similar to an acid, but not exactly the same. If it gets in your eyes, it can cause blindness in those eyes at those higher concentrations. The oxidizing power does a real number on your cells. Now, in addition to hydrogen peroxide, there are also a number of metallic peroxides that are out there and used quite commonly. Which lab did you do on Friday? Okay. So your lab this week is going to be about oxidizers. You're going to get a chance to look at and work with some metallic peroxides on your lab on Friday. In particular, you'll look at sodium peroxide. Now, metallic peroxides have the same kinds of issues that other peroxides, organic peroxides do. The only real difference is that these peroxides don't usually form some kind of flammable component when they decompose or when they react. They will give us oxygen. That oxygen gas can be used to fuel a fire or to cause the spread of some other kind of chemical reaction. But we don't tend to see them a whole lot with anything other than, well, just these kinds of decomposition. One thing that we will notice, though, however, is that when these substances come into contact with water, in addition to giving us that oxygen, we also get a base. So we get a corrosive and an oxidizing agent upon decomposition. And so what you'll actually see in the lab on Friday is that corrosive power, because you'll see as you interact the sodium peroxide with water, how it forms that sodium hydroxide and how it bubbles up to form that oxygen. Now, you'll be doing it in a relatively controlled setting. You'll have far more water than any kind of oxygen that you'll create. So relative danger to you is pretty small. You're going to do this reaction in a test tube. But nonetheless, if this were occurring out in the open atmosphere, out in kind of the real world, non-laboratory kind of situation, this could be potentially dangerous. We've seen what sodium hydroxide can do. Think about that Coke can experiment that we showed you about a week and a half ago. Some other examples of oxidizing materials. Metallic hypochlorite. Hypochlorite is an ion. In particular, it is the OCl- ion. These kinds of molecules are very, very common for bleaches. And in particular, we think of things like sodium hypochlorite, NaOCl. This is what we call common bleach or Clorox. We also have calcium hypochlorite. Which is known commercially as HDH. Now you go to any kind of store that sells household home improvement goods, and you will find these two chemical agents on the shelf. In addition to bleach, which is used for laundry, for disinfecting, for a number of different purposes. We also find bleach as a component in things like drain openers. So when you look at something like liquid plumber or Drano, what you'll see in there is a combination of two reagents, sodium hydroxide, lye, and sodium hypochlorite, bleach. Now, why those two in particular? Well, the primary reason is you've got a corrosive that can react with a lot of different materials and help to unplug the drain through chemical action. And you've got a oxidizing agent in the hypochlorite that can react with the other stuff. And unlike acids, which would probably eventually eat through the walls of your plumbing, we know from our corrosives unit that most bases are incapable of eating through metal. Only certain types of metal actually get involved and react with bases. HPH, calcium hypochlorite, you tend to see this at pool supply stores. Where we tend to see it used most often is for if you're disinfecting your pool, if you're disinfecting your hot tub, or any kind of large amount of water. HPH is the way to go for that. Talking specifically about sodium hypochlorite, again, the trade name for this is Clorox. Clorox is a 6% solution of sodium hypochlorite. That is its patent concentration. There are other versions of it. Hexachlor, for example, can be up to anywhere between 10 and 12.5% of sodium hypochlorite. We see now in a lot of household generics the uses of what they are calling more heavily concentrated bleaches, bleaches that are more splash-free. And what they've done in those cases is they've concentrated them by removing some of the water, and they usually put in some kind of a chemical stabilizer agent to help thicken them up a little bit so that they don't splash as much. This is by far the most common use of this particular class of oxides. We find this all over in a number of different applications. Again, especially now, any kind of disinfecting wipe that involves bleach of some kind probably has some amount of sodium hypochlorite in it. Now, there are other kinds of disinfecting wipes out there, but the ones that specifically say that they contain bleach have this particular compound on it. And they are good at killing bacteria. They are good at sanitizing workspaces. Calcium hypochlorite, as I mentioned before, its trade name is HPH. This is used in larger scale kinds of cleaning applications. So you go to the YMCA and you use their pool, whichever pool it is. They're disinfecting it using HPH. You have an in-ground pool at your house, probably using HPH in some form or fashion as the primary disinfecting agent. Now, if you have something smaller like a hot tub or like a small above ground pool, you're probably not using HPH. You're probably using those floating tablets. Those floating tablets are usually not HPH. They're usually something else. Was that? Some of them can be iodine. I've seen more with bromine. I've seen other chloride compounds used, just not sodium hypochlorite. And the reason why you would avoid calcium hypochlorite or any kind of large-scale bleacher in those cases where you have smaller amounts is because it actually just puts too much into the water. It's very difficult to regulate this in small quantities. This is used for larger scale kinds of things. Again, look at the examples there on the slide. Sanitizing the drinking water for a city. The disinfecting a municipal swimming pool. Doing things like sewage treatment, where wastewater comes in, it goes through a process of flocculation and filtration and whatnot to remove the stuff that you don't want in there. And then it gets blasted with calcium hypochlorite to kill anything that didn't just fall to the bottom. And it gets sent back out to the end consumer. So this is one of the most common agents for that kind of large scale disinfectant. Again, if you're looking at a smaller scale, you have a hot tub at home, you have a small swimming pool at your house, or at your neighbor's house, they're probably not using this particular pool chemical. Probably using some other application that is very, very similar, but not nearly as potent. In particular, they're probably using one of these. Di- and trichloroisocyanuric acid, or di- or trichloroisocyanuric salt. These are the things that usually come in powder form or tablet form. What happens is they are basically a salt, but once they dissolve in water, they basically free up all of the available chlorine, and the chlorine goes out into the water and acts as a disinfectant or acts as a bleaching agent. Where we see these most common are things that are so-called dry bleaches. So things that are powdered but claim to be bleaching agents of some kind. And then no, we're not talking about stuff like OxyClean or other kinds of oxygenated cleaning agents. We're talking about stuff like powdered dishwashing detergent. So if you have a dishwasher and it uses a powder to run the dishwasher, more and more dishwashers are going away from this, but some still do it, and that's why they're still sold that way. Things like Comet. You've ever used Comet to scour your bathtub or your sink or some other surface in your house? That tends to have dry bleach in it. That's why you're not supposed to do it with your bare hands. I'll just leave that look alone, Josh. I'll just leave that look alone. Other things. Yeah, I'm unsure of this one. Barkeeper's Friend might have some of the same kinds of agents in it. I'm not as familiar with that one. I do know Comet does. I don't know if that one does or not. The idea is kind of the same. If you've got a scouring agent, they usually contain one or more of these compounds to act as a bleaching agent, to act as an oxidizing agent. The oxidizer goes in there, helps break apart the substance to make it easier to clean. We also see these in industrial sanitation products. In commercial applications, things that you can buy at the store, they would come either as sodium or potassium salts. And again, these are the so-called chlorine tablets. So I don't know how many of you own or know someone who has a pool or a hot tub, but if they got a small one, you've probably seen this little floating bobber in the pool itself, and that's what contains the disinfectant. So that just kind of floats around in the pool, and as it does, it is slowly dissolving these chlorine tablets to help keep the pool water disinfected. If you're working with a hot tub, it becomes especially important that you do something like that, because water in a hot tub never really gets hot enough to kill bacteria, and bacteria like warm things. So if you're not careful, your hot tub can be a warm bath full of bacteria just waiting to get at you. Why hot tubs in particular are so much maintenance. You really have to want one and want to put in the work to maintain one to have one. All right, some other common oxidizers. Chlorine dioxide, ClO2. This is a gas product. It is extremely unstable, and the reason for its lack of stability comes mainly from the fact that it is going to have an unpaired, unshared electron. So, drawing right here. So this unpaired, unshared electron on the chlorine here, this is the source of that reactivity. Remember, anytime we have an unpaired, unshared electron in a molecule of any kind, it is going to be especially reactive. It is going to try to pair up that electron in any way that it can. And that's why it is unstable. Now, as far as what it does with its lack of stability, it is known to cause respiratory damage. So if you breathe it in, it starts reacting with your lungs to get that extra electron, does some damage to your cells as it does. If it gets into your eyes, same thing. It can cause some pretty nasty damage to your lungs and your eyes as it goes through your body systems. As an oxidizer, it is 2.5 times more powerful than chlorine. Now, we already know that chlorine is a pretty powerful oxidizer. It has a lot of commercial applications for us. This is even worse. And so, one of the common applications for chlorine dioxide is as a microbiocide, meaning we do some kind of chemical reaction that releases chlorine dioxide into the air, and that stuff basically kills any microbes that are in that room. Think of it almost like a fumigator, but just for microbes. All right, let's get into some more fun kinds of applications. Fireworks. Now, as I mentioned before, when we were talking about the different classes of fireworks, the common compounds that are involved in the creation of fireworks are usually in the chlorate family. So we're talking about chlorites, which in this case is to be sodium chlorite, NaOCl2. Oops, excuse me, wrong formula. NaClO2, sodium chlorite, NaClO3, sodium perchlorate, NaClO4. Now, as we saw in our classes of oxidizers, the more oxygens we add to that compound, the stronger the oxidizing power is. Chlorates and perchlorates were designated as strong oxidizers, Chlorites were actually in the moderate oxidizers category. But it is these compounds that are ultimately going to provide the source of oxygen to make that explosion occur at the appropriate time. Because basically all a firework is an explosive that is on a time delay. The only difference between it and a time delayed bomb or any other kind of explosive on the ground is that we shoot it straight up into the air first, as opposed to at some sort of terrestrial target. Is that? Well, you're right. The quantity of explosive here is somewhat limited as well. It's a controlled explosion as opposed to an uncontrolled one. So again, the chlorate family here, whichever one is used, that is going to be the driving force. That is going to generate the oxygen necessary for the combustion reaction to occur. Now, the other stuff that we add is either a combination of fuels, things that'll actually burn to make it go boom, or substances that we add to enhance the overall effect of the firework once it does explode. One of those substances is magnesium powder. Now, we talked about magnesium when we talked about our flammable metals. What color does magnesium turn when it is burned? Okay. It's a really bright white. So the purpose of magnesium powder is to provide a greater illumination, to give us a brighter color. Now, if the magnesium is left by itself, then what we get are basically those flashbang fireworks, the ones that give us a short burst of white light and a big loud sound. But if it's not one of those, then we usually use magnesium just in a small quantity to help the other colors kind of shine out. Because otherwise, they'd be kind of hard to see, especially against a dark sky. Think about how blue fireworks look. They kind of get lost in the shuffle, especially if there's not a whole lot of brightness behind them. With the magnesium in there, that magnesium helps that blue light to kind of burst and shine so that you can see it against the dark picture of the sky. Other effects, aluminum flakes can actually help to produce those luminous tails. So what we're talking about is one of two things: either the sparkly kind of look that happens as it is shooting up for certain types of fireworks, or that kind of long-lasting effect of the fireworks kind of falling down and those sparks just kind of bursting out once the main explosion does occur. That's aluminum at work. Almost always that aluminum burning has kind of a reddish orange kind of color to it. If you remember our discussions from Friday, when we talked about potassium, that coloration is specific to the element that is involved. So part of the flame lab that you did on Friday, you had to do the flame tests, right? So you took the solid barium solution and you put it in the fire and the flame turned green. Well, that's one of them. Or you put strontium in the fire, it turns red. Calcium, it turns reddish orange. Sodium turns yellow. Potassium turns purple. Those characteristic colors can be used to help identify elements, or in the case of a firework, can help to produce different kinds of coloring effects. Now, in terms of the fuel that is involved in fireworks is primarily carbon and sulfur. Carbon and sulfur being two of the primary components in the powdered explosive there. As we talked about, the chlorate class of compounds involved are the oxidizers. These compounds will react in a manner such as this to produce a good measure of oxygen. That oxygen can then react with the carbon and the sulfur in the black powder to create carbon dioxide and sulfur dioxide. That sulfur dioxide, again, if you remember our discussion of sulfur-based compounds, when we talked about flammable solids, sulfur dioxide has that burning hair smell to it, that burning rubber smell to it, and that's what creates that sulfury kind of smell that comes out, usually that kind of hangs over the area after a fireworks show. So we've kind of covered the bases here. Primary fuel is carbon and sulfur. Primary oxidizer is some sort of chlorine. We've talked about how we add certain types of materials to it to give it a certain kind of coloration. Now comes the fun part. How do I get the different colors? So if I don't want just the plain old white magnesium burst, how do I get a red? How do I get a blue? How do I get a purple? Well, the answer to that comes into additives. There are certain kinds of compounds I can put into the firework that will create different kinds of coloring effects. And the color effects that are associated come mostly on the back of the metal ion itself. The characteristic colors that we see tend to be a combination of the metal that is present inside of the powdered mixture and the amount of energy, the amount of oxygen that becomes available to it. So, for example, barium. When barium absorbs a ton of energy, you know, kind of like the energy that we would expect from an explosive reaction or a large-scale combustion reaction. Again, I want you to think about that poor gummy bear roasting away to death in that test tube. The reason why it was flashing purple was because the combustion of that gummy bear was producing so much energy that the potassium ions that happened to just have been there were absorbing some of that energy. Their electrons were jumping up in energy, and as they came back down to where they were supposed to, they gave away some light. And that light happened to be on the purple end of the spectrum. That phenomenon is not just for potassium compounds. Any metal ion that is present at the time of the reaction can do the same thing. Absorb some energy, get those electrons all excited, and release energy in the form of light when those electrons come back down to where they're supposed to be. The color we see just happens to be a byproduct of how much energy that those electrons ended up absorbing. So in the case of potassium, the energy that is emitted is relatively high energy. It comes off as purple light. Purple light is the most energetic form of light that we can see. For sodium, it comes off as yellow. For strontium, for lithium, they come off as reddish. For calcium, it comes off as reddish orange. For barium, it comes off as kind of yellow green. For copper, it comes off as blue. So adding in these metal compounds allows us to get that color effect that happens when these fireworks burst. Because the burning of the carbon and the sulfur is going to produce lots of heat, lots of energy, and these metal compounds are just going to be caught in the crossfire. And as they absorb some of that energy from some of that combustion, they end up releasing some energy along the way as well. Now, in addition to that, we also have to consider the overall kind of perspective of combustion. The more oxygen that we have available for this combustion, the better chance we are to get complete combustion of that carbon and that sulfur. If I have complete combustion of the carbon and sulfur, I'm going to see flames in the blue region rather than the yellow region. Think about what happens to your Bunsen burner flame. You turn on that flame. If it's just reacting with the oxygen, if you haven't, or with the air, if you haven't opened up that barrel to let extra oxygen in, all that it does is it just burns a little bit at the top. You've got this big yellow flame. If through chemical action, the end product is just going to react in the air, we tend to see more stuff in the red, yellow, or excuse me, the yellow-orange region of the color spectrum. But if I have enough of these chlorates present, that it actually produces some excess oxygen, and I have plenty of oxygen available to do the reaction itself and burn all of the carbon and sulfur completely, the resulting flames from that reaction, from that combustion, are going to be blue. And so we see usually this delicate kind of mixture where we know we need some amount of chlorate, but maybe not as much if we're trying to get something that's more yellow or green or red. We don't want the blue to obscure that. But if we want blue and purple, we want to make sure we've got plenty of oxygen in there, because otherwise that yellow flame is going to show up and maybe my blue firework doesn't appear blue anymore, because there's not enough oxygen to completely burn off everything. So fireworks are a really cool kind of application of a lot of the things that we've talked about up until this point. Because we've got in here oxidation. We've got the reduction of fuels. We've got combustion reactions. We've got flammable solids. We've got metals absorbing energy and releasing it as light. We've got a lot going on here. And a firework puts that all together in one classified as explosive package. Now, this same kind of logic gets applied to non-explosive fireworks as well. So if you want to think about sparklers, Sparklers work on this same kind of premise as well. One of the most popular 4th of July fireworks bought every year are sparklers because they really don't require a whole lot of anything to set up. You can do them pretty much anywhere. And the relative danger of using them is considerably lower than for others. It means that they're good for kids. But they work on the same kind of premise. White sparklers primarily contain magnesium compounds. Ones that have colors, we usually utilize one or more elements from our color wheel here as a means of getting the different colors to come up. And sometimes, there are certain kinds of sparklers out there, rainbow sparklers, that'll actually go through a number of different colors in succession. Maybe it starts off as white, then becomes red, then becomes green, then becomes yellow, then becomes blue. How they get that is they basically just stack little bits of those compounds on top of each other so that as the substance burns down, it ignites a new metal and gives it a new color. So the chemistry of these is actually really, really fascinating. All right, I've got about 2-3 minutes. We'll end today by talking about perchlorates. Now, perchlorates are the same kinds of oxidizers that are found in those fireworks. We're talking about substances that have the perchlorate ion, ClO4- on it. The reason we are concerned about them is that perchlorates have started to find their way into groundwater sources. And since they're finding their way into groundwater sources, that means that they're finding their way into certain types of drinking water surfaces. There's a lot of people in this country use well water or other kinds of sources connected to well water for their primary means of drinking and cleaning and other things. Even certain municipalities, take Vincennes, for example. Our municipal water comes from 2 sources. One source is the redistribution of wastewater. Another source is the purification of water from the Wabash River. It is a combination of the 2 that gives the community its source of water. Well, the water that's coming in from the Wabash will have runoff from the ground, which means that the perchlorates that might be in the groundwater might find their way into the Wabash as well and find their way into the city. Here's the real reason that we're concerned. Consumption of perchlorates can cause damage to your thyroid gland. It can also cause neurological problems and a number of things that are related directly to growth and development for children. This is especially true for the unborn and for the young. So consumption of perchlorates by the mother can ultimately affect the baby inside of her. Make it so that the baby doesn't grow properly, doesn't have the correct developmental hormones, that can end up stunting the growth of the fetus or making it so that they have some health problems when they are born ultimately. And that is where we will stop for today. On Wednesday, we'll finish up chapter 11 here, talking about more different applications of oxidizers, and we'll end up with a discussion of matches. Matches being kind of the all-in-one product that contains fuel, oxidizer, and a starter in some cases. Have a great day.